Hi, I'm Joanna Wu, and I'm from the ETH Zurich, and I will be talking about quenching, mass, and morphology or structure as it relates to quenching, and I've been doing this work in collaboration with this list of people here. So as we know, the galaxies are bimodal, and one of the big questions that we're going to be talking about in this session is how do they quench? And there are several quenching models that have been proposed. As somebody mentioned, there are at least 5 or 6 or 7, I don't know. So let's just review quickly some of them. Viral shock heating in halos greater than a critical mass of about 10 to the 12 in halo mass. Now this is the basic idea is that infalling gas is shock heated at the viral radius and then eventually cools to the center. And the shock eventually collapses for less massive halos, but in massive enough halos, the shock is stable and the cooling time is long, preventing star formation in the central. That's the idea. Of course, viral shock heating doesn't naturally predict the many observational studies that have shown that quenching correlates with morphology or structure. So several bulge building or density building mechanisms have been proposed, and we heard about many of them yesterday, including gaseous inflow to a compact region or bulge that induces a starburst, which then exhausts all the gas, leading to a quenched object. And gaseous inflow can happen either through major mergers or through a gravitationally unstable disk, or both, as we heard yesterday. There's also morphological quenching, the idea of which basically is that the presence of a bulge stabilizes the disk against a star formation. Of course, there's AGN heating as well, which succeeds in bringing specific star formation rates low as we see in the observations. Now, viral shock heating, of course, is related to the halo. The bulge building mechanisms which are related to the morphology, are processes that happen in the galaxy. AGN heating seems to be more efficient in hot halos. So this could be a coupling between the external halo and internal galaxy process. Now, satellite galaxies can experience any of these quenching mechanisms while they were centrals before they fell in, and may continue to experience these quenching mechanisms after they fall in. But they also experience other mechanisms such as ram pressure stripping, tidal stripping, and harassment. I won't get into the details of these mechanisms, but this was just an overview of some of the things that have been proposed. So I have separated quenching mechanisms into two broad categories: an internal process, which could be related to the bulge, and the external process, which is related to the halo. Obviously, there may not be such a clean separation, but for the purposes of this talk, we're separating them. So here I have then, so I'm going to be studying these quenching processes in the Sloan. And here I have the density, the stellar density within the inner kiloparsec of a galaxy, the sigma 1 from Fang et al., and halo mass from the Yang et al. Catalog, which is really group mass, the group mass of the group that a galaxy is in. And this is just for central galaxies. Now here I've plotted the logarithmic density contours of the satellites, and as you can, of the centrals. And as you can see, there's a correlation between sigma 1 and halo mass for central galaxies. Now I'm going to turn these contours white and plot underneath them a color scale, which represents the quenched fraction of galaxies. Now, as you can see here, the black contours, by the way, the black contours follow the color scale. So what you're supposed to see here is that at fixed halo mass, the quenched fraction increases very strongly with sigma 1. But at fixed sigma 1, the quenched fraction increases very weakly with halo mass, if at all, perhaps a little bit over here and maybe over here. Okay, but it's weak. Now let's take a look at the equivalent plot, but now the color scale is specific star formation rate and not the quenched fraction. So remember, quenched fraction is a bimodal quantity. Specific star formation rate is more continuous. And here you see the dependence on the halo a little bit more strongly, up here and maybe over here. Now, the specific star formation rate is a bimodal quantity, so this this color represents the mean, and that could be misleading because this green strip here, it doesn't mean that they're all in the green valley. It means that there's a comparable number of galaxies that are on either side of the bimodality. Okay, so let's actually look at the distributions of specific star formation rate. I'm going to take a strip of constant halo mass and find the distribution of specific star formation rate in bins of sigma in this strip. So that's this plot here. So these galaxies are all in that vertical strip, and blue to red means increasing sigma 1. So as you increase your sigma 1, your blue peak goes down and your red peak goes up. Very simple. That explains why the quenched fraction goes up very, very strongly with sigma 1. Now, if we take a horizontal strip in this diagram, so a fixed sigma 1, and plot the specific star formation rate distribution in bins of halo mass. So here we have increasing halo mass from blue to red. And what you can see here is that the distribution remains basically the same shape, but the entire distribution moves leftward towards lower values of specific star formation rate. So let's also look at low and high values of sigma 1. So, oh yeah, so I've done the same thing now, but I've taken a lower strip, and you can see here that the trend continues onward. By the way, this trend continues also at fixed stellar mass. Didn't mention that, but it does. So if you remember, the bimodality is split basically right here at -11. So this plot shows you that if you don't have any quenching related to sigma 1, the halo mass will decrease your star formation rate in such a way that you don't really even see a bimodality. It just goes straight through the green valley. Okay, so for completeness, I also show the upper portion of the plot. And here are the bins of halo mass. And again, we see a decrease in the mean specific star formation rate. So to summarize the results for central galaxies, sigma 1 correlates strongly with the quenched fraction. Sigma 1 predicts the shape of the specific star formation rate distribution. The halo mass correlates with SSFR in contrast. And the halo mass predicts the shift of the specific star formation rate distribution without changing its shape by much. Okay? So how do we interpret this? Here's a proposition. The increase of the quenched fraction is related to the transfer across the bimodality. So let's say it's quick. There's a valley. It seems to be a quicker transition. The decrease of specific star formation rate, in contrast, is related to a slower fading of star formation. And therefore, the quenching that's related to the sigma 1 process is fast, and the halo-related quenching is slow. So this is an interpretation. There could be other interpretations of this data. But this makes sense. Why? Because viral shock heating is expected to cut off accretion, but remaining gas is expected to continue forming stars. Timescales of consumption can be roughly 2 to 3 gigayears or even higher. However, mechanisms that result in high sigma 1 are expected to be violent. For example, violent disk instability and major mergers. Once gas is consumed, the halo could play a maintenance role of quenching, preventing new gas from falling in. Now, these ideas can be tested in a SAM, and I did that. I used the Gallic SAM, which implements quenching due to viral shock heating and bulge quenching independently, but in such a way that the original implementation was that shock heating removed all gas from the galaxy as well as cut off accretion, so the opposite of what I'm saying. And bulge quenching cut off accretion but left the gas in the galaxy to continue forming stars. So exactly the opposite of what I think is going on. And this is the plot of sigma 1 versus halo mass that this model predicts. And the contours are exactly the opposite of what we see. So if we just switch these two senses of the quenching, then we get this. And the contours look much better compared to the observations. So this simple test in a SAM is encouraging and may be pointing to the correct interpretation of the data. Okay, so that was centrals. Now let's talk about satellites. Satellites, so I here have sigma and halo mass as usual, and I've split the satellites into bins of those that lie in the outer halo, those that lie in intermediate ranges from the center, and those that lie very near the center of their group or halo, and colored by the quenched fraction. So as you can see, the quenched fraction increases very strongly with sigma 1 in the outer halo, but there is a non-trivial halo dependence also here in the outer halo. But as you move towards the inner halo, the quenched fraction increases strongly with halo mass at fixed sigma, but at fixed halo mass, the quenched fraction does not increase very strongly with sigma. So let's take a look now. We talked about the quenched fraction. Let's take a look now at what the specific star formation rate is doing. Now this is specific star formation rate versus sigma 1. Okay, so I've changed the axis a little bit. This is similar to, so if you remember from yesterday, the compaction diagrams were all about this L-shaped compaction route and then the quenching. Now I've gone and flipped it so that star formation rate goes up. All right, so up here is star forming and down here is quenched. Okay, that's just to keep you awake. Now, I've put the centrals here. Actually, they're isolated galaxies, but these are centrals. These are satellites in the outer halo, and these are satellites in the inner halo. I put all the masses together in this plot. I will separate them later, but I put them all, and you can see already that this inverted L shape is a little different for these satellites. They seem to be, if they seem to actually be quenching first before compacting. Now, these diagrams were made at constant mass, so let's take a mass slice and look at this diagram. So here we have the inverted L, and here we have the distribution of satellites in this axis. And so as you can see, that the slice of stellar mass in Jerome's paper was originally meant to isolate perhaps an evolutionary track, because when you quench, you're not expected to change your stellar mass by much. So that was the motivation for postulating that compaction happens, then quenching. Now, here the satellites seem to be going down this graph first, quenching, and then perhaps compacting. But remember that these galaxies here may have been quenched while they were centrals. Okay, and they may be experiencing quenching, central type internal quenching, while they are in the halo as well. Okay, so before I go on to talk about the excess of satellite quenching, I'm going to show you what this plot looks like. It's not a very, I'm sorry about the quality. So the contours are still there, they're in white now, but now I've colored the plot based on the mean halo mass. And so for the satellites, what you're supposed to see is that if you're in the bottom part of the plot, your mean halo mass is higher. Okay, so keep that in mind. So now, what I wanted to do then, assuming that the process that is quenching centrals is separable from the process that is quenching satellites, I took this density contour plot and subtracted the density contours of the centrals to get the excess of quenching that is due to the environmental process, the process that happens when a satellite falls into a halo. Okay, and so I took the white contours from the centrals and I've put them here. So the centrals, the centrals are now these white contours. I've just copied them over, and now this color, it measures the excess of and deficit of satellite galaxies. The green means a deficit of galaxy satellites, and the pink and white mean an excess of satellites. Now, there's some normalization here, so if I had normalized the star-forming main sequence to be the same number density, then this would have popped out a little bit higher. Now, this is all work in progress. I'm very happy to accept comments and suggestions to think about all this. But what I want to point out here is that this excess of satellites, of quenched satellites, is offset from the quenched centrals by about 0.3 dex. So let's look at this excess a little bit more closely. So I've taken the galaxies in this plot, both centrals and satellites, and taken a look at the magnitude, the light in the bulge, inspired by the work of Marcella that she just presented. I'm going to take a look at the light and mass of both bulge and disk. So here's the bulge distribution of light. So bright is here and dim is here. The red histogram is for the satellites and the black histogram is for centrals. And as you can see, the distribution of light in the bulge is basically the same. Okay, so how about the mass? This is the stellar mass in the bulge, and the distribution of satellites is red again, the distribution of centrals is black, and they're also very similar. Maybe there's a slight offset to slightly lower bulge masses in the satellites, but I'm not sure that's significant yet. And this is still work in progress. Okay, so let's look at the disks. What are the disks doing? This is the distribution of light in the disk. Satellites are in red again, isolated or central galaxies are in black, and the satellites seem to be dimmer than, the satellite disks seem to be dimmer than isolated disks in this square, remember, okay? What about the masses? The distribution of stellar mass in the disk seem to be the same between satellites and central in this box. So what we see here, what I think I'm seeing here, this is all very preliminary and work in progress, and what I seem to be seeing is what Marcello was talking about, is disk fading. Disks are the same mass, but their light is dimmer for these satellites that are in this box. So in summary, in the outer regions of halos, sigma 1 correlates strongly with the quenched fraction, where satellites have probably only recently fell in. Oh, I forgot to mention that interpretation of that plot. But satellites only recently fell in there and have not had time to experience slower halo quenching. But by the time they get to the inner regions of halos, the halo mass correlates with quenched fraction, whereas sigma 1 does not. The quenched satellites have lower sigma 1 than quenched centrals of the same mass and of the same the same mass and the same star formation, right? And if you look at that little region of the plot, their bulge light and mass are comparable between satellites and centrals. However, the disk mass is also comparable, but the disk light is dimmer. And that's it. Thank you.
All right, questions, and could the next speaker come get set up? Go ahead.
So, the plot with sigma 1 and halo mass was just for the centrals was fantastic. And what I wanted to ask though, so I mean, you made the point that sigma 1 was strongly correlating with the quick quenching event, and then you said the halo mass is correlating with halo quenching or whatever. But it seems more like the halos regulate the star formation rate rather than the quenching. It's not as if the fraction that do nothing was changed. It's just that I do a little bit less. It's like getting older, but it's not like dying.
Yeah, okay, you could say that.
I feel that that's more of a kind of regulation. The same way that morphological quenching is actually really regulation of stuff. I can still use my gas, I just can't use it very well.
Right, so
what's your kind of reaction to that? And then there's a minor thing about, I'm actually not sure about the amplitude of that.
Okay, yeah, I mean, the word quenching I have been using to describe both the fading and the sudden cutoff or sudden drop. You could possibly, if you want to distinguish between those two processes and call the sudden drop quenching and the other one something else, fading or aging,
the reason
that's
I
fine.
want to call it quenching is because we actually don't know what the future of those holds. Without a quick quenching event, it may be that those would continue to form stars for another Hubble time, but just at an increasingly low rate. I think that the word quenching implies a future that we don't necessarily know. That's my particular concern.
Fair enough, yep, thank you.
All right, one more quick question.
Can you just make a quick comment of clarification that maybe also goes in the direction of your question before? As you can see, even in this law, the sigma 1, sort of between the central and the satellites, gives one picture, and the bulge mass, however, gives another picture. So I think we have three chances, things that, well, yeah, they're slightly different. Let me finish and then it's for discussion. But I think we have three ways ahead. One is we believe in sigma 1 and not in bulge mass, and one is we believe in bulge mass and not in sigma, we believe in both, in which case we make this